So in section 6.1, for 6.2 and also for 6.3, I'm sorry, I put together some steps that you want to try to use as you solve by power series. Hopefully, as you go along, um, the steps would become commonplace. Looking at the steps just by themselves make no sense. Right? Typically, with any type of math, math is better understood with the problem. So I'm going to apply these steps to the problem that we'll work here, and then I'll move hastily into the next section, because the next section, the way you solve those problems is identical to this right here. So steps to solving a differential equation using a power series. First step is to get a common index. I may just say, find a k factor. And then the second step, whatever that x to the k term is, you want to factor it out. When you do that, the goal is to be able to write, if you have several summations, maybe 3 or 4, it doesn't matter, you want to be able to write all those summations as one summation. Well, you're going to do that if the terms in the summations are alike, if there's some kind of commonality that you can factor, make one summation. The goal is to be able to solve for the C sub k. In some kind of sense, is there a formula that I can get for C sub k? It's going to be evident from whatever you have in those summations. We're going to look at that, be able to extract from there some formula for C sub k. Now here's the question of philosophy. Well, maybe not philosophy, but that should have been my major. Here's the question. What is C sub k? I'll tell you what C sub k is. And C sub k is most dang on important here. These are these constants that we have in our solution. One, if it's an integral and you say plus c, that plus c is dang on important. And then going back here for differential equations, for the superposition principle, when you write y is equal to c sub 1 times y sub 1 plus c sub 2 times y sub 2, and so on and so on, that c sub 1, c sub 2 that we would have for the so-called solution for differential equation, this is what we're going to be solving for. Those guys are hard to get. So I was saying before, you just can't throw away the constant as if it's nothing. It really means a whole lot. Okay? It's almost if to say that you can't throw away your childhood. Okay, you're an adult. Well, some are, and you have your own responsibilities now. But if you think about it, our entire beings as adults hinges a whole lot on when we were little. Think about it. Whether it be good or bad. Most of our adult experiences hinges on when we were 5, 6, 7, 8, 9, 10, 11 years old. So you just can't throw it away as if, So here are the steps. Number 35. In problems 35 and 37, solve each differential equation in the manner of the previous chapters, and then compare the results with the solutions obtained by assuming a power series solution of the form. Okay. Trying to grab you. I didn't know it was like that. Okay. All righty, good. Let's solve this just from something of how we solved these problems a long time ago. So we solve here, this is y prime is equal to 5y You know that this is dy over dx is equal to 5y. Separate the variables. So this implies that 1 over y times dy is equal to 5 dx. Integrate both sides. And so we have the natural log of the absolute value of y is equal to 5x plus some constant. We can exponentiate both sides, and that gives us y is equal to e to the 5x times e to the c sub 1. We can let c equal to e to the c sub 1. So y is equal to some constant times e to the 5x. Do you recall Taylor's expansion for e to the x? The summation is n goes from 0 to infinity of x to the n divided by n factorial, right? Okay. So if I have e to the 5x, then I just replace the x with 5x. So this is the summation as n goes from 0 to infinity of 5x to the n over n factorial, or you can write it as the summation as n goes from 0 to infinity. You can factor out the 5 from the x, and that'll be 5 to the n times x to the n all over n factorial. So if you put a constant in front of that, then our solution that we will get when we solve this problem by the power series will look very similar to this guy with a constant in the front, because here for this particular problem y is equal to a constant times e to the 5x. So let's begin. So now we solve y prime minus 5y equal to 0 by power series. And here we assume that y is equal to the summation as n goes from 0 to infinity of c sub n times x to the n. We assume that the y itself can be written as a series, here a power series. Well, if that be the case, this is y. I'm going to replace that y here with the power series. I need to replace y prime. So looking at the power series, y prime then would imply that this is the summation as n goes from 0 to infinity. The c is a constant, multiply it times the term, so you take the derivative of x to the n. That's just n times x to the n minus 1. So I take the problem is y prime minus 5y equal to 0. I'm going to replace the y and the y prime with this power series representation. So this becomes the summation as n goes from 0 to infinity. This is y prime, so this is c to the n times n times x to the n minus 1. And this is minus 5 times y, but y is the summation as n goes from 0 to infinity of c sub n times x to the n. That's equal to 0. Okay. So I hadn't done much there. Just replaced what we have for the problem with power series representation. Now, in the steps, the first thing we said is I want to get the common index or a k factor. Let's see how we do that. And I think before I even go there, let's call it red. Look at this first term. This is the summation as n goes from 0 to infinity. This is c sub n times x to the n minus 1. If n is equal to 0, right, then for that first term, this is a summation, so I'm adding up several terms, right? Adding up, what happens at n equals 0, plus what happens at n equals to 1, plus what happens when n is equal to 2, and then so on. So for the very first term, when n is equal to 0, for this guy, notice that first term comes out to be 0. Not the whole summation, but just that first term, right? Because of this n sitting right here. If n is 0, then 0 times the rest of those terms there, the c sub n times x to the n minus 1, is going to give me 0. So it's safe to say here, for this particular summation, I can start this guy at n equal to 1, and from 1 to infinity, without any loss of generality. Okay? Because that first term at n equals 0 is 0 anyway. Right? Doesn't happen over here for this summation as n goes from 0 to infinity of c sub n times x to the n. Because I don't know what, if I plug in n equal to 0, I just get c sub naught times x to the 0, which is just a negative 5 times c naught. I don't know what c naught is. C naught becomes a constant from the superposition principle. So it's safe to say here that I can start the first summation at n equal to 1 without loss of generality. So if that be the case, then you can say that this is n goes to 1 to infinity. Everything else stays the same. C sub n times x to the n minus 1 minus 5 times the summation as n goes from 0 to infinity. C sub n times x to the n. That's all equal to 0. Now, I want to get my k factor. So first step here is to get common index. K factor. Here's how I introduce it. You look at the exponents there. This is n minus 1. And then this guy right here is x to the n. So I'm going to for the first summation, let k equal to n minus 1. For the first summation. And let k equal to n, what I'm looking at. I'm looking at the exponent. Okay. So when I do that, I'm going to have, let's say, I got that statement there, let. So if I have here for this first one that k is equal to n minus 1, let's see if I can write it here. And then over here, k is equal to n. So that be the case for the first summation. I have k plus 1 represents n. Obviously, nothing happens over there. So look at the summation, and I'm going to replace the n's with the k factor. So the summation, when n goes from 1 to infinity, well, if n is equal to 1, then this is k is equal to 1 minus 1. So k goes from 0 to infinity. This is c sub n, but n is k plus 1. Pardon me? Because n is equal to 1, right? N starts at 1. So if n is 1, then k is equal to 1 minus 1. So k starts at 0. And so we come back up here. This is times n, but n is k plus 1 times x to the n minus 1, but n minus 1 is k. So this is times x to the k. Minus 5, 5 in summation. Minus 5 times the summation. Here, since k is equal to n directly, just replace the n with k. K goes from 0 to infinity. C sub k times x to the k is equal to 0. Okay. Now, two things you want to make sure you observe, because the next step is to write the summations as one summation. And I can do that because this common index would be common for this summation, the first summation, and the second summation. That x to the k, right? X to the k is here, x to the k is there. I can do some factoring. I'm not going to factor it out of the summation. I'm going to factor it within the summation. Because remember, the summation is over the iterations of k. So I can't put any k term on the outside of the summation, but I can factor it on the inside. So two things we're going to look at. One, you make sure that x to the k is the same for all the summation, so I can do some factoring. Secondly, you want to make sure that you're starting at the same position. Then you can factor. Now, some of the problems, they're not going to be at the same position. You say, hey, how did this happen here? We're at 0, and this guy's at 0. Actually, for the first term, since it looks like you went down 1, you actually added 1 to that summation, to that infinity at the end of it, which is okay, because infinity plus 1 is still infinity, right? Or if it was infinity minus 1, well, it's still infinity. So you can manipulate the beginning, you're manipulating the beginning and the end. You don't care about the end, right? Who can get to infinity? Okay, so if those two are the same, k goes from 0 to infinity for the first summation. K goes from 0 to infinity for the second summation. That's the first thing. Right? Second thing, x to the k for the first summation, x to the k for the second summation. I can do some factoring. So here, we're going to factor out x to the k. Let me say factor it out. It's not actually going out, as you will see right here. this is what I have. Factor out x to the k and write all the summations as 1. So this is the summation as k goes from 0 to infinity, bracket c sub k plus 1 times k plus 1 minus 5 times c sub k, close the bracket, times x to the k is equal to 0. Again, x to the k is still confined to the summation, right? So we've written these two summations as one summation because we had some commonality. So this is the same thing as the previous statement, right? Just did some factoring. And as I get older, just like wine, I get better, So if I list like maybe 7 steps, up there, what I had like several years ago, it may be confined now to about 2 or 3 steps. So, because I may be combining a couple of steps into one, but it's okay. That's the joy about, if you know what you're doing, you can manipulate it. Right? If you don't know, then then you're boxed in to a particular form, and the form has more authority than you. If you know what's going on, you control it. Right? I had an example, but it's not good, so I was trying to explain something to my son about driving, and so, well, you can do this, EJ. Well, you really can't, but anyway, it's a bad example. I know what I'm doing, EJ. All righty, so step number 3. I want to get a formula for this c sub k plus 1. Basically, I want to just get this guy by itself. Here's what we're saying. The summation of all these terms here within this summation has to equal to 0. Right? Well, I'm not making any choice for x. I don't know what that is. So, but I do know that when k starts off at 0, you get whatever terms x to the 0 is 1. Something has to make this entire summation equal to 0. More than likely, it's not x to the k. It's going to make it equal to 0. What's going to make this guy equal to 0 is going to be these constant terms right here. If you remember how we built up the Cauchy-Euler, when you had, summation of these constants, whatever, then times some x term, it was the same argument here that if the solution is on an interval from 0 to infinity, open at 0, those solutions are talking about the values for x, so x would not be 0. But what's making this summation 0? It has to be these constant terms. So what I want to do is to step 3, get a formula for c sub k plus 1. Whatever the biggest term, k, maybe k plus 2. So if it's k plus 3, c sub k plus 3, then I want to get a formula for the c sub k plus 3. If it's c sub k plus 2, get a formula for the c sub k plus 2. Because obviously anything before that would help you produce the next recursive constant term, or recursive coefficient term, I should say. So step number 3, get or write a formula for c sub k plus 1. I'm going to get a formula for that guy right there. All right. So here's what we have. So I have c sub k plus 1 times k k plus 1 minus 5 times c sub k is equal to 0. It's what's inside the brackets that will determine the summation to be 0. And here, this is provided that the solution is on an open interval from 0 to infinity. That's the solutions for x. Right? So if that be the case, solve for c sub k plus 1. C sub k plus 1 is equal to 5 times c sub k all over k plus 1. Now, the next step is that I want to be able to produce all the coefficients to be able to write the solution. What is C sub 0? What is C sub 1? What is C sub 2? What is C sub 3? You can go out to about maybe 6 or 7 terms until you kind of get a pattern. And so the idea, do you recall, you would get that same pattern when you did Maclaurin or the Taylor expansion. There you were having to do each derivative, first derivative, second derivative, third derivative, plug in C equal to whatever it was given, that your center that was given. So here we're able to solve for these coefficient terms based on the recursion. So here we'll start let k equal to 0, and so we get c sub 1, and we can solve for c sub 2 and so on. Let's see. So step 4. Solve and get a solve for so if k is 0, C1 is equal to 5 C0 all over 1. Or just 5 C0. If k is equal to 1, C sub 2 is equal to 5 C sub 1 all over 2. If k is equal to 2, C sub 3 is equal to 5 C sub 2 all over 3. If k is equal to 3, C sub 4 is equal to 5 C sub 3 all over 4. Let's do one more here. If k is equal to 4, C sub 5 is equal to 5 C sub 4 all over 5. All right? You see what I did? Right? Now, let's look at that. Some of these guys would depend on a previous one. Let's see where that is. So C0 seems to be an initial condition or initial point. C sub 1 seems to be an initial value. Well, let's see here. This is C sub 1, but C sub 1 here, no. C sub 1 depends on the previous guy. C sub 2, that is, depends on the previous guy. Let's look at this. This is 5 over 2 times C sub 1, but C sub 1 is 5 times C0. So this guy is 5 squared all over 2 times C0. Well, C sub 3 depends on C sub 2. And so C sub 2 is given to be 5 to the second divided by 2. So this is 5 to the third all over 3 times 2 times C0. the next one, c sub 4 is 5 times, well, 5 divided by 4 times c sub 3. C sub 3 is what's given before that. So this is 5 to the 4th over 4 times 3 times 2. Do you see what's happening in your denominator? We're getting factorials, right? You see that? This is, let me write it out. Then when I come back, I just write the simplification of it. This is 5 divided by 5. I'm going to leave it there just to look at the pattern. This is 5 divided by 5 times c sub 4. So c sub 4 is the 5 to the 4th. So this is 5 to the 5th times c naught all over 5 times 4 times 3 times 2. That's just 5 factorial, right? So let's see. So this guy right here is 5 to the 2nd over 2 factorial times c naught. This is 5 to the 3rd over 3 factorial times c naught. This is 5 to the 4th times c naught all over 4 factorial. And well, c sub 5 is 5 to the 5th all over 5 factorial times c naught. Right? Now step number 5, watch this. Step 5, write the solution in the form y equal to c naught plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x to the 3rd plus c sub 4 times x to the 4th plus, and so on. You get the pattern, right? I mean, where does that pattern come from y? That's what you assume in the beginning, right? Remember, we said assume assuming y equal to the summation as n goes from 0 to infinity of c sub n times x to the n. Isn't that what that is? Right? Yeah. If you let n equal to 0, you get c naught x to the 0 is 1. Plus, if n is equal to 1, you get c sub 1 times x to the first power. Plus, if n is equal to 2, you get plus c sub 2 times x to the second, right? Doesn't like my dot, dot, dot. Never happens on a chalkboard. But anyway. All right, so now on the previous page, what I'm going to do is we got to just replace C naught, C1, C2, C3, and C4 with what we just found in those coefficients on the previous page. That's all. So we don't have anything for C naught, but everything else depends on C naught. That's good. So we have y is equal to C naught plus C sub 1. C sub 1 is 5 times C naught. So this is 5 times C naught times x. I just replace the C sub 1 with 5 C naught times x. Now plus C sub 2. C sub 2 is 5 squared divided by 2 factorial, right, from the previous page. And I think they all had that pattern, right? C sub 2 is 5 squared divided by 2 factorial, C naught. C sub 3 is 5 to the third divided by 3 factorial, C naught, and so on. So we see the pattern. So this is 5 squared over 2 factorial, C naught, times x squared, plus 5 to the third over 3 factorial, C naught, times x to the third, plus, just write one more, then see the pattern, 5 to the fourth over 4 factorial, C naught, times x to the fourth, plus and so on. The pattern looks like this, plus 5 to the n times x to the n all over n factorial, plus and so on. So this is y is equal to, factor out C naught. I have left 1 plus 5x plus, yes, 5 squared times x squared over 2 factorial plus 5 to the third times x to the third over 3 factorial plus 5 to the fourth times x to the fourth over 4 factorial, and so on. Do you see what this is? This is y is equal to C naught times the summation as n goes, how do we produce the 1? Let n equal to 0. N is 0 to infinity, and this is 5 to the n times x to the n over n factorial. Or, this is C naught, yes, times the summation as n goes from 0 to infinity of 5x to the nth power all over n factorial. Isn't that the same thing when we solve by hand? That was the same solution. Let's go back and find it. Y was equal to some constant times e to the 5x. And what's e to the 5x? The summation as n goes from 0 to infinity of 5 times x to the nth divided by n factorial. Isn't that the same thing? So our point is that solving by the power series takes a very long time, right? Well, no, that's not the point. That's left out. Okay. The point is this, that the solution for the power series is the same solution that you would get if you were solving, with the previous method. So, but now later on, like I told you in the beginning, later on when we start solving some of these differential equations where there is no known solution method, like we don't have separation of variables, or we don't have the linear form or homogeneous and that kind of thing. So a lot of times you'll be left with maybe two possibilities to solve. Power series, which, if you're in a lab, if you remember all that stuff, you can work it out, about the power series, or just use a sophisticated computer or program. Any questions there? What I want to do is, I want to work another problem. It works identical to this guy, but it's from the next section. Let me show you that. Oh, by the way, let me go back and look at, see how I manipulated these steps. So we got to get a common index, replace n with some k factor. The second thing we did was to want to factor out that x to the k term. And see, I put steps 2 and 3 together, write all the summations as one summation. And then once you did that, you want to try to find a formula for c sub k. And then you solve for those coefficients. Solve for each one. What is C sub 1? What is C sub 2? C sub 3? You see the pattern. And then from there, you can write the solution in this form. Just replacing the C sub 2 with those coefficients that you got from above and replace the C sub 3, C sub 4, and that kind of thing.